So welcome everyone. I'm Anne French from Wellington Astronomical Society, and I'm delighted to welcome you to this year's Beatrice Tinsley lecture. Now, while we're waiting for our co-host, Dr. Yvette Perrott from the Victoria University of Wellington Astronomy Department to arrive, I'm going to tell you some things about our speaker tonight, Professor Anna Scaife, and then when Yvette arrives, she may or may not tell you about Beatrice Tinsley, who is, until very recently at least, New Zealand's foremost cosmologist, sadly deceased in, 1980, something like that, 81. So here we go. So let me tell you about, here we are. So this is the very person we need. So do you want to talk about Beatrice? And I'll introduce Anna, or do you want to go the other way around? So as you can see, Yvette has just come from a graduation ceremony.
Just for the occasion.
Yeah, a pretty grand entrance, I have to say. That's fantastic. So I'd also like to mention she always dresses like that. Come on in. You're not late. So do you want to speak at this point and on behalf of Victoria University say how great it is to have everyone here?
Sure.
Excellent. So I'm wearing Adam's mic, but you can put on. Good. Okay. And there's the extra stuff there if you want to.
All right.
Yes.
So huge welcome to everyone here. Sorry for my very late appearance. I did my best, but crowds at graduation plus Uber plus traffic did not equal getting here on time. So it's a really great pleasure to welcome our Beatrice Tinsley lecturer for this year, Professor Anna Scaife from University of Manchester. Just to tell you a little bit about the background to the Beatrice Tinsley lectures. They are an annual series of public lectures that the Royal Astronomical Society of New Zealand hosts. So we get fantastic speakers from around the world, like Anna, to come and give us a series of public lectures all around the country in different places about an interesting current topic. And so these are named after a fantastic researcher named Beatrice Tinsley, who she was raised and went to undergraduate university in New Zealand, and then went overseas to the US. She was an astronomer who was one of the first people to really study galaxy evolution, studying how galaxies evolved and changed over time, and that led to a lot of that led to some discoveries about cosmology. And so she really pioneered the study and changed our view of cosmology in some fundamental ways. And it's quite amazing that she comes from New Zealand, and we should celebrate her more than we do. So very nice to have this opportunity to tell you a little bit about her as well. So I will pass over to Anne to introduce Anna.
Such fun.
Good.
Thank you so much. And I want to tell you about Professor Anna Scaife, who is terrific, and we're so proud to have her here. So she's a professor of radio astronomy at Jodrell Bank Centre for Astrophysics. And she's also one of the 5 inaugural AI Fellows of the UK's Alan Turing Institute. So all Alan Turing fans. She has worked at Southampton, the Dublin Institute for Advanced Studies, and also Cambridge University. Did she bump into you at Cambridge, Yvette? Yes. Exactly, that's right.
BHT examiners.
Wow. Went okay, did it?
Yeah.
Yeah. Cool, okay. Fantastic. So interestingly, she's part of a team working on the Square Kilometre Array radio telescope. Had a talk from one of the people in Western Australia who's deeply involved with the SKAs last year, I think maybe July, August, something like that. That was a fascinating talk. She led the design of the computing and storage for the European SKA Regional Centre, which means she's terrifically clever with large amounts of data coming down a hose and needing to be processed as fast as you can do it. And what do you do with the rest of the data? Throw it away. Huh? It's enormous, isn't it?
You squash it.
You squash it. Okay, right. Okay, cool. She's currently the UK representative to the International Union of Radio Sciences for Radio Astronomy. She's Deputy Editor-in-Chief of the Royal Astronomical Society's Techniques and Instruments journals. So if you're interested in putting a paper into that, charm her later. She was honoured by the World Economic Forum in 2014 as one of 30 scientists under the age of 40. Those things are a bit embarrassing when you get past the age of 40, aren't they? But she was, one of the 30 under the age of 40, selected their contributions to advancing the frontiers of science, engineering or technology in areas of high societal impact. She was awarded, I'm going to get you to pronounce it, the Blau Chair. The Blau Chair of Astrophysics at the University of Groningen, I can't do my G properly, in the Netherlands for excellence in research, broad knowledge of astronomy, and an outstanding international status in astronomy. And in 2019, she also received the Jackson Grill Medal of the Royal Astronomical Society, which is awarded for outstanding invention, improvement or development of astronomical instrumentation or techniques. Now, I'm betting that the technology and instrumentation and techniques that they awarded you the prize for is not what they originally thought they were going to be, like when the prize was set up. I'm guessing it's an old prize with old tech. That's right. So that's quite cool. So the topic for tonight is how artificial intelligence is changing the way we do astronomy and why that's not necessarily a bad thing. And I'm delighted to welcome Professor Anna Scaife to talk to us this evening. And off we go, handing over.
Need 2 seconds. So thank you, Yvette. Thank you, Anne, for the very, very warm welcome. It's a pleasure to be here to talk to you today. So yes, I'm going to talk about how AI is changing the way that we do astronomy and why that's not necessarily a bad thing. For those of you in the audience who were at the Rasmus conference last weekend, the first bit of this talk may seem familiar, but we will go in a different direction. So I like to start all of my talks by actually turning this around and asking you a question. So by a show of hands in the room, can I ask how many people here are using AI in their daily lives? Okay. Yeah, so a reasonable number, I would say 60 to 70%. Yeah, so I think that's a very high level of self-awareness in the room about AI. For those who didn't raise their hands, I'd like you to take a look at these logos and think about if you use any of these on a regular basis. So you'll probably recognize some of them straight away. We've got our voice activated services, so anything with a voice activation. We've got our Netflix, Amazon, Spotify, anything that makes a recommendation to you or predicts what you want. Social media, it's a given that there's AI under there. It's not only showing you things using AI, it's also stealing your data to design AI. Mapping apps. Used one to get here this evening. Anyone recognize these ones in the middle? Yeah. So these are apps that are largely used for education and sort of writing, helping people to learn. What about these ones? Anyone recognize these? No. Yeah. So these are the health. They are health. Yeah, so these are generally not as well known. So you might not be using these, but your doctor is probably using something, not necessarily to make decisions about healthcare, but in an assistive capacity in their work. So having seen all of these logos, can I ask for a show of hands again? Well, we'll skip the show of hands, but. So the point I'm trying to make is that even if you don't realize that you're using AI in your daily lives, at this point, most of us are, because it's pretty much ubiquitous in anything that we do digitally at this point. And most of what we do these days has a digital component. So AI has become a part of daily life. So now everyone is comfortable with what AI they're using. Can I ask why we use AI in our daily lives? And this is more of a shout out the answer type participation. You don't have any choice. That is increasingly true.
Summarizing text to reduce the word count.
Summarizing text, that's a very specific example, yeah. More generally, productivity, yeah. Smarter.
Code correction.
Code correction, yeah, again, a specific example, but all these things are efficiencies, right? Yeah, we use AI because it makes our lives easier. And I think that's exactly why we should use AI. But we have to think a bit carefully about what it is we're using AI to make easier, because there are some things in our lives that we would like made easier using AI. And then there are other things which are, undeniably easier, but perhaps would be better done by people. So there was this great quote that originated on social media and got picked up by the press by this writer here. And she said, "I want AI to do my laundry and dishes so that I can do art and writing, not for AI to do my art and writing so that I can do my laundry and dishes." And I think this is very true. A lot of the AI that we see being produced actually is not replacing what people originally thought AI would replace. People thought that AI would replace, either manual jobs or technical jobs. And in fact, what we've seen is that where AI is, replacing most employment is in the creative industries. And I would argue that those are the areas where, the human element is most important. And so we should think quite carefully about where we let AI into our lives. Otherwise, we stand to lose some of that humanity. And I think the same is true for science. So when we use AI in science, we want the AI to do the tedious, handle-turning bits of the science that have to be done to get to the exciting analysis that allows us to make the new discoveries. We don't want to end up with us doing the handle-turning bit so that the AI makes the exciting discoveries, because that's just the wrong way around. So what I'm going to talk about today is AI that does the boring bit, or not necessarily boring, but the really laborious bit that actually makes up 95% of science. Because when you read about the glossy discovery in the magazine, you can guarantee that that was the last 5% of the effort that went into the project. The first 95% was going through data, changing data formats, making images, cleaning up images, calibrating telescopes. And no one wants to write about that, because that's not the bit that goes wow, right? But it is an integral part of the process. And it's actually really important these days that we can automate that part of research. The main reason why it's become important in the last, I would say, decade is because the volume of data that's being produced by astrophysical observatories has grown so hugely. And this is largely due to the effect of digitization, high-speed digitization in astronomical observatories. So if we look at the data rates coming out of some modern observatories, so here's an example. So the top one and the bottom one are radio observatories, the middle two are optical ones. And there's some data volumes that you can see there. So sort of, Euclid, hundreds of gigabytes per day. Everyone's probably reasonably familiar with a gigabyte of data. All the others are in petabytes, which is, I think people are generally have an awareness of petabytes. Astronomers talk about petabytes like they're nothing. But these are huge volumes of data, and I'll clarify exactly how big a petabyte is in a second. And not only are they huge volumes of data, they're also very complex data sets. So whereas historically, in a single observation, we might have had one galaxy clearly in that observation, and then, a bit of background stuff. These days, if we make an observation, we have thousands to millions of astrophysical systems in a single observation. And so that complexity combined with the volume of data really means that if we want to be able to extract science from that data in a timely fashion, we need to be able to do it in an automated way, because doing it by eye just doesn't scale. And as that kind of by eye handle turning bit is usually given to grad students to do. And as a colleague of mine likes to say, there might be enough grad students in the world, but there certainly isn't enough coffee. So the result of this is that we've seen this exponential rise in the number of publications in astronomy that use artificial intelligence. So this is just showing you the numbers of publications that include the words machine learning, deep learning, or artificial intelligence in that abstract or title, which means it's an underestimate because lots of papers use these things and don't put it in the abstract or title. So just to make sure that everyone is sort of on the same page about that data size, like I said, astronomers talk about petabytes all the time. So I'm picking the final number of this list here, which is for the square kilometre array telescope. So the square kilometre array is going to produce 600 petabytes of data per year. That's the compressed data products. So just to clarify, I'm going to sort of give you an idea of how big exactly is one of those petabytes. And the short answer is that it's about 3.5 years of your life. Because if you recorded yourself every second of your life, 24/7 in high definition for 3.5 years, then the video would be about 1 petabyte in size. The human brain has been estimated to store about 2.5 petabytes of memories. And you can also put that in terms of digital photos as well. So that's the context that we're working in. So 1 petabyte is 3.5 years of your life. And the SKA is producing 600 petabytes per year with an expected lifetime of 50 years. So that's...
What's the exponent for a petabyte? Is it 10 to the what?
It's 10 to the 18.
Okay, thank you.
Yeah. Wait, yes. No, 10 to the 15. Sorry, I went up to X there. 10 to the 15. Yeah. We're going to go to zeta later.
Well.
So it's a lot of data. And this is why AI is becoming, absolutely essential for extracting that information in an automated fashion. So obviously, first thing I did when I wanted to talk about AI and astrophysics is I asked ChatGPT, what should I talk about? And ChatGPT, it's very self-affirming, asking ChatGPT questions. ChatGPT gave me a list of examples. This is actually this is GPT-3, so it's a little bit old. They're all very vague. I am actually going to talk about the second one, which is image analysis, because I think that's very accessible in terms of understanding what the AI is doing. Would I talk about the other ones? I could do. I'm not sure that they're the ones I would pick, but ChatGPT seems to think they're interesting. So I'm going to talk about how we apply AI to astronomical images. So this would be called a computer vision problem in a standard computer science sense. And a lot of what I'm going to talk about is going to boil down to understanding what the image is of. So that is a classification problem in AI terms. And I thought I would just start by explaining a little bit about how AI does classification. So to those of you in the audience who know how AI works, take a nap for a couple of slides. This is my simplified overview of how an AI classifier works. So if we have some images, and I'm gonna go with cats and dogs initially. It's very important to classify cats. Apparently. Did you know that there are 6.5 billion images of cats on the internet? Yeah, it's crazy. Before the large language models took off, approximately 10% of the world's internet traffic involved cat pictures. I mean, what does that tell you about us? An alien civilization looking at our internet traffic would make some very strange assumptions, but they would confirm everything that cats think. About their own importance. Yes. So for an AI classifier, the image that you put in, the pixels, are the features. And we pass that to some AI model, which contains a bunch of parameters which are learnable. the AI model condenses the information in our image into what we call a latent representation. And then it uses that latent representation to predict an answer. And we tell it which answers we want. So if we're doing cat versus dog, what we need to start off with is a large volume of images of cats and dogs, each of which has a known label. So we need to know, is it a cat or is it a dog? So if we say cats are red points, dogs are blue points, then initially when our model's not trained, then the latent representation is not meaningful. What we want our model to do is to be able to separate out the red dots from the blue dots. So for example, to move all the red dots above the line and all the blue dots below the line. And we achieve that by iteratively passing our data through, comparing the model's predictions to our known labels, and then using the difference between them to update the learnable parameters in the model. And we do that as many times as we need until we achieve a suitable degree of separation between the points, where everything above the line is now classified or predicted as a cat, and everything below the line is predicted as a dog. And then we have a trained AI model, and it's ready to be, released into the world. So that when someone uploads a new cat picture to the internet to make it 6.5 billion and one, the internet can use the AI model to say, yes, this yellow point from our new data sample is above the line, and therefore this is a cat. Now, the drawback of this kind of classifier is that if we upload an image of something else, the model doesn't know about this thing. It only knows about cats and dogs. So when we put it through the model, it will still give us a yellow point somewhere in that space, and it will still give us an answer. And it will be completely confident in its answer, and it will tell us that this is a cat. So that is a bit of a shortfall. And it's one of the things that motivated the development of some of the newer AI models that you're probably more familiar with, such as large language models, like the GPT model, which is what underlies the ChatGPT service. And has anyone used this one? Yeah, DALL-E. So this is an AI model that generates images from text. So these kinds of models are called foundation models, and they're built on a slightly different premise. So in a foundation model, we have broadly similar schematic, but we train them using data that doesn't have any known labels. So it would be just the pictures without the cat or dog labels. And we train our foundation model to give us a latent representation again. But instead of drawing a line to classify things, that latent representation is more of a spectrum, where it just groups together more similar types of inputs. And what we would hope is that, cats end up in one area of that latent representation and dogs end up in another area. And if we put in something new, like our meerkat, it won't tell us it's a cat. It'll simply tell us it's more similar to cats than it is to dogs. So it understands the degree of similarity between our different inputs. And that allows it to do a wide variety of things instead of just a single yes/no task. Another really nice thing about these models is that if you do want to ask a specific question with a specific answer, you can take your foundation model and refine it using a very small amount of data where you do know the labels. And this is a process called fine-tuning, where you add a small label data set and it's able to separate out different groups of data. And computationally, the advantage of this is that whereas training the original model is very computationally expensive, doing this fine-tuning is actually computationally very efficient and very cheap. So it allows you to make very powerful analyses for specific tasks in a very accessible way. So at this point, you're probably thinking, I thought this was a talk about astronomy. So let's get to that. So just as we are all desperate to classify images of cats, it's also very important for us to be able to classify different types of astrophysical objects from our incoming data. And as I said earlier, one of the ways we do this historically is to use graduate students. And where graduate students don't scale to the problem, we've also used citizen science. So has anyone used the Galaxy Zoo service? Yeah, we've got a few people. Okay, some people are only half admitting to it. There's not going to be a test, don't worry. So Galaxy Zoo is a citizen science project where you log in on the internet anonymously if you want, and it shows you a galaxy, and then it asks you some questions about it. Things like, is this a spiral galaxy? Is it a blob? Is it an elliptical galaxy with no features? How many spiral arms does it have? Is there a bar in the middle of this galaxy? So simple morphological questions that you actually don't need to know a lot about galaxies in order to answer. And in total, Galaxy Zoo asks citizen scientists about 200 questions, and millions of people have answered these questions about hundreds of thousands of galaxies. It's been a fabulous resource. And this has basically provided the largest labelled data set in astrophysics to date. It's just short of a million galaxies. So the kinds of things you might see within the Galaxy Zoo look like this. So you can see that all of these galaxies have their own, they're like people. They have their own features, they have their own morphologies. They also have their own colours. So the colour tells us about broadly the age of the galaxy. So galaxies start off blue and young and star forming, and then as they age, they get redder. And at the end, they're sort of red and elliptical, and we call them red and dead. But the colour is important because it tells us what stage of their evolution they're in. And in fact, we measure models of galaxy evolution by counting the number of galaxies with different colours as a proxy for learning how long they stay in different stages of their evolution. So we can use an AI model to answer the Galaxy Zoo questions in exactly the same way as we can use an AI model to classify cats and dogs. So here I'm going to talk about an AI model in the foundation model sense. So if we train an AI model using all of the citizen scientists' answers on the Galaxy Zoo data set, when we take a new survey, we can then take one of our new galaxies, put it through that trained model, and just by looking at its position in that latent representation, we can immediately get the answers to all of the questions that were asked in Galaxy Zoo without asking anyone else. There is a slight nuance here, which I just want to make everyone aware of. So when it gives us the answers to those questions, it's not telling us about the intrinsic properties of the galaxy. What it's telling us is, what would a citizen scientist tell us about this galaxy? So it's like a proxy citizen scientist, if you like. So just to show you what that might look like, here is a schematic of that latent representation for the Galaxy Zoo data. So this is trained on 300,000 galaxies with 10 million labels from citizen scientists answering questions. And you can see that the distribution of galaxies groups together similar looking galaxies. So in the bottom corner, we have our edge-on galaxies. In the other side, we have our spirals. At the top, we have our blobby ellipticals. And if we encode this galaxy through the model, then it ends up where the red dot is. And that tells us which galaxies it's most similar to. Now, obviously, I've undersampled this space here. You're not looking at 300,000 galaxies across this space. If we did use all of the 300,000 galaxies, it would look a bit like this. So every dot is now the position of a galaxy as seen by this AI model. Just to really make that clear, you can see the shapes between the two. Now, one of the reasons that I'm showing you this is to highlight the red points. Now, in the Galaxy Zoo service, the citizen scientists asked all these questions, but they also have a free text box to make comments about the galaxies, so they can describe things that aren't asked in the questions. And they even have conversations about the galaxies. It's a really useful source of information. And one of the things that people point out on Galaxy Zoo is when a galaxy just looks a bit odd. Now, these text comments are not included in the AI model's training. So the AI model doesn't know about the text comments. But when we colour code all of the galaxies that have been described as odd in Galaxy Zoo, we can see that the AI model has actually grouped them together, even though it wasn't given this information to train the model. So the model has essentially learned something new without being told about it during its training. And this is useful for multiple reasons. Firstly, because it's very cool. But secondly, because we can then go and look at these galaxies and say, well, why are they odd? And if you look at those red dots, the odd galaxies, they broadly fit into one of three categories. So we have galaxies that are merging with each other. So these are interacting galaxies. Galaxies that have very irregular morphologies. So ironically, irregular and odd are different things. If you like astrophysics. And then we have these ones in the middle, which are ring galaxies. So these are galaxies that have star formation around their central core, but it's not in spiral arms. It is literally what it sounds like. It's a ring of star formation around a central bulge. And these ring galaxies were thought to be quite rare. In fact, until very recently, we only knew about a few hundred of them. And that was just because people assumed that there weren't very many of them. They were difficult to find. You know, the graduate students weren't optimized for ring galaxies. But using the AI model, once we knew what we were looking for, we could fine-tune it using a very small number of these ring galaxies in order to find more. And so that's what we did. So here's a gallery of some of those ring galaxies. And in fact, we found not just a few hundred, but we found 40,000 of these ring galaxies. And this was something that the press really liked because it was like the Terminator of astronomy. It was a cyborg astronomer, apparently. It was not our words. But astrophysically, it was also really interesting because these galaxies are not blue or red, they're green. So they sit in this intermediate stage of galaxy evolution called the Green Valley. And as I said, understanding the number of galaxies of different colors tells us about, you know, the time that galaxies spend in a particular stage of galaxy evolution. So knowing that there are way more green galaxies than we previously thought was actually very important. And since we did this, there are now big catalogues of ring galaxies emerging, which is really nice. More recently, the same model that we trained using the Galaxy Zoo data has actually been deployed as part of the observatory processing for the Euclid satellite. So Euclid is a satellite that was just launched in 2023. It's an optical and infrared satellite. It's got a 1.9 meter mirror on it. And its objective is to survey about a third of the entire sky. Scientifically, it's aiming to constrain the nature of dark energy. And it's going to do that by basically looking at the shapes of galaxies. So understanding the galaxies that are detected by Euclid is very important. And just this 1 month ago, Euclid released its first catalogue of galaxies. And these are not from the full 1/3 of the sky. These are just from some early science fields. And that's what I'm showing you here. You can see the images are full of galaxies, right? There are millions of galaxies in here. And the first catalogue that was released from the Euclid satellite used our model to basically distinguish the different morphologies of the galaxies. So this is called the Euclid Quick Release 1 catalogue, which contains about 400,000 galaxies. So that is about 0.5% of the 100 million galaxies that are expected to be detected by Euclid, which will be large enough to morphologically distinguish. So I think Euclid is expected to detect 2.6 billion objects in total. And you can see that the model has done a similar thing. So you've got your edge-on galaxies, you've got your disturbed galaxies, you've got some galaxies with strong bars, which is the linear feature in the middle of those galaxies. We can say exactly how many spiral arms. The model can distinguish between numbers of spiral arms. And this one was quite interesting. Again, so this is These are galaxies that the model predicts to have morphological features, but no spiral arms. And when you look at them, it turns out that these are actually all groups of galaxies. So there are multiple galaxies in each of these. The other thing it was able to separate out were instrumental artifacts. So this is not an astrophysical source. It's an aberration in the data from the telescope towards particular directions. And so this actually helps you to improve the performance of your telescope as well as doing the astrophysics. So this has been really nice.
I'm sorry, does the model give you the distance as well?
No, so to get the distance, you need to look at the spectral data to get the redshift.
Doesn't do that.
So it doesn't do that. There are now models that do cross-modal embedding, so cross-modal representations that take spectra and images and allow you to predict redshifts. But this model doesn't do that particularly. Those models are very much in their infancy at the moment. Yeah.
So you guys have built a foundational model that is able to catch patterns that the human being cannot see by themselves. That's what you're saying.
So the human being probably could see them, but wouldn't be able to find as many of them in the data as easily. Yeah.
Oh, so what this model does is merge those data sets together and shows you, oh, there's this pattern that you guys might miss because there's so much data.
Exactly. Yes, exactly. Or whereas, if you spend, so I think we estimated that if you sat an astronomer down and asked them to look at individual images and tell you what they were, they could get through about 120,000 a year if that was their entire job.
They cannot see the patterns, right? The sequences.
They can't navigate the data in the same way that the model does. So the model can give you 1 million predictions in a second. Yeah.
How long it took you to build this model to train it?
To train the model, it actually doesn't take that long to train it. It takes days on our computer.
You guys built it in your lab?
Yeah.
Wow. Congrats.
Thank you very much. I wanted to go away from the optical data a little bit at this point and show you some other applications that we've been doing in this area. So the optical data from the Galaxy Zoo Citizen Science Project is very nice because it gives us this very large labeled data set that allows us to build a very informative model. But in other areas of astronomy, we don't have all of those labels. And in particular, in radio astronomy, we have very little labeled data. So we have a huge volume of data, but very few labels. We live in this paradox where we simultaneously have too much data and not enough data. But we still need to do morphological analysis of radio sources. Now, radio sources, I think, are less intuitive for a lot of people. Right? People generally have a good concept of what a spiral galaxy looks like, what the Milky Way galaxy looks like. So I wanted to kind of introduce you to radio sources. Now, this is not a radio map, this is an optical map. So those of you who observe might recognize that these spokey patterns, that means these are stars, they're in the foreground of the image. And then a lot of the things in the background are galaxies external to our own galaxy. And in particular, I want to highlight this one in the middle, which is a weird woofly galaxy. In fact, this is a giant elliptical galaxy. Anyone recognize it? No? Okay. Yeah, no, it's good. I wouldn't. So this is Cygnus A, which is a very massive galaxy, and this is what it looks like in the optical. But if we look at it in the radio, it looks like this. Thank you very much. So in the center, we just see a point. And this point is the supermassive black hole at the center of the galaxy. And supermassive black holes work by accreting material. And due to conservation of angular momentum, they have to then eject material. And that ejection of material happens in highly collimated jet structures that emerge from either side of the black hole. And those jets basically shoot away at ultra-relativistic speeds, so very, very close to the speed of light, and they slam into the surrounding intergalactic medium near the galaxy. And that's what causes these bright points that you can see at the ends of the jet, so these are called hotspots, and then the material in the jet flows backwards from those hotspots, and that's what these lobes are. And so what you're seeing here is radio emission from the ultra-relativistic particles that have been accelerated by the supermassive black hole. And this is synchrotron radio emission. Now, Cygnus A, if you ask a radio astronomer what kind of radio galaxy this is, that
FR2.
it is an FR2 galaxy. It's a Fanneroff-Rayleigh class 2 radio galaxy, which means nothing to anyone apart from radio astronomers. So there are many types of radio galaxies, but historically we've divided them into two main morphological types. So the FR2s, like Cygnus A, which have this characteristic highly collimated jet, and then the lobes on the ends of the jet, and then Fanneroff-Rayleigh class 1 sources, which look different because they are actually brighter at the base of the jet, and then the jets look more like smoke. And we still don't understand the reason for this split in morphologies between radio galaxies. So whether it's due to the intrinsic nature of the black hole being different between these two types, whether it's due to the environment around the galaxies, or most likely a combination of the two. So understanding that difference is actually very important for understanding how these galaxies form and evolve, and more generally, how the structure in our universe grows. Now, not all of them look like these nice canonical examples that I'm showing you on the left-hand side, right, where most radio astronomers could just go, oh, yes, that's an FR1, that's an FR2. These galaxies, like optical galaxies, all have their own individual characteristics. So I'm showing you a sort of a zoo of them here. And you can see that these two at the top, FR1s, this one is an FR2, FR1 here, this one's an FR2. This one, neither. X-shaped galaxy is what we would actually say. Yeah, so it's, that some of them just don't fit the mold. So designing AI that can group these galaxies is not only useful for testing our models, but in fact, it's useful for redefining the classification, because this FR1, FR2 classification is historic, it's subjective, it's from humans trying to basically separate out things that aren't really necessarily separate types of galaxy. They're just useful morphological types that really represent some point on an underlying spectrum of physics. So hopefully the spectrum of the latent representation we get will be, useful to do that. And that is one of the drivers for the science behind the Square Kilometre Array telescope that's already been mentioned. So the SKA will be the world's largest radio telescope. It's 2 telescopes, the first of which looks like this. It's in the Northern Cape of South Africa in the Karoo region. And this is a centimetre wave radio telescope. So in total, there'll be 197 dishes across Southern Africa. The first 64 dishes are up and running and already taking data. The beauty of building telescopes like this, which are arrays of dishes rather than just one giant dish, is that you don't need to wait for them all to be there before you can start using it. You can just add in dishes as you go.
What's the effective gain of all those antennas together?
Oh, what, in dB?
Yeah.
I don't know.
Quick question.
Yeah.
Do you get a really high gain narrow focus so you can scan? Is that how it works?
So with these dishes are about 15 meters across. And yeah, the field of view is basically the Fourier transform of the dish on the sky. So depending on the frequency, it's going to be a few arc minutes.
So they sort of scan the sky.
Yeah, so they sit on an axis and they move. These ones. Yeah. The other part of the telescope looks quite different. So this is the low frequency component of the Square Kilometre Array. And this is based in Murchisonshire in Western Australia, which is the land of the Wajiri Yamatji people. And this is a very different technology. So here you can think of each of these stations of dipole antennas as being equivalent to one dish in the other telescope. And in total, there will be 150,000 of these antennas in Western Australia. And I was just there last week, and I got to see some of the first stations that have been built. So each of these antennas sits about this high. It's like a Christmas tree shape, to the extent that there is one in the office that gets decorated at Christmas. The individual antennas see the whole sky instantaneously, but we apply an electronic phase across each of the stations, which allows us to form a beam in a particular direction on the sky. So there's no mechanical movement at the front end of this telescope. And we call this, well, people refer to telescopes like this as a software telescope, because the power of the telescope is not in the front end hardware, it's in the computer behind it that actually does the analysis. I would argue these days that in fact we should be calling them AI telescopes, because the data from these two telescopes is 300 petabytes a year per telescope, so 600 in total. That is the compressed data. If we stored all of the data, the raw data from the low frequency telescope, we would be storing 5 zettabytes of data per year. So that's 10 to the 21 bytes. That's just ridiculous, right? It doesn't make sense. So we do compress the data, which means we do lose access to some science, right? We have to make a choice. But even at the data rate we have, which is about 10 terabits per second out of each of the telescopes, we still need that automation in order to do the science. Oh, and I have a little animation of that. Yes. So yeah, data rate of 10 terabits per second goes through 2 stages of computing, one actually co-located with the telescope, and then another one where the images are made, which is in a supercomputing facility in country. So in Perth for the Western Australia telescope, and in Cape Town for the South African telescope. And as I said, the South African telescope is already operating. So this is one of the Meerkat dishes. So 64 dishes, the first 64 are called Meerkat. And this is what they look like. This is not an artist's impression. This is a photograph of one of the dishes. And this is one of the first images from the first surveys. It's called the Mighty survey. And similar to the Euclid images, you can see that there are thousands of objects in this image. The difference is that here, everywhere you see a bright point, you're basically seeing a supermassive black hole. And some of them, you can even see the extensions from the jets and the lobes. And if you zoom in, you see it on many, many of them. So this is where I'm gonna finish my talk. I have been talking about the many advantages of AI for astrophysics, and I just wanted to end with a caveat, which is that obviously we know already, particularly from societal applications of AI, that AI encodes bias, and when a model tells you an answer, even though the model is very confident, doesn't necessarily mean it's right. So in fact, a lot of the work that my group does is not just building the models, but also understanding the uncertainties associated with the predictions from the models, and identifying the biases that they introduce. And this is very natural for astronomers because we spend a lot of time understanding the biases that our instrumentation introduces into our analysis, and we simply have to do the same thing for our AI models. So I'll finish there. Thank you for listening, and I'm very happy to take any questions.